Hi, I'm Pen from Salesforce Research. It's my honor today to introduce our proposal learning approach for semi-supervised object detection. We all know that semi-supervised object detection trains object detectors on both labeled and unlabeled data, so it can benefit object detectors from large-scale unlabeled data on Internet. For labeled data, it is straightforward to use ground truth labels to get training information, but for unlabeled data, due to the unavailability of ground truth labels, we cannot train object detectors on unlabeled data directly. So we propose a proposal learning approach to train object detectors on both labeled and unlabeled data. Here we focus on proposal-based object detectors, also known as two-stage object detectors, which first generate proposals in the first stage and then generate proposal features and predictions in the second stage. More specifically, we focus on improving the second stage by learning proposal features and predictions from both labeled and unlabeled data. And we propose a self-supervised proposal learning module and a consistency-based proposal learning module to achieve our goal. Here is the architecture of our framework. Here, red arrows correspond to the computation of standard fully supervised learning losses and are only applied to labeled data. As we can see, for labeled data, we could use the standard fast RCN pipeline to train the network, like the standard RPN loss and the standard RCN loss. For unlabeled data, we first add the noise to proposal convolutional features and then pass this noisy proposal convolutional features through the RCN network to generate noisy proposal features. So noisy proposal features and their original proposal features share the same convolutional computations. Then these noisy proposal features and the original proposal features are fed into the self-supervised proposal learning module to compute the self-supervised proposal learning losses. Also, we compute the proposal predictions from both noisy proposal features and the original proposal features, and feed these proposal predictions into the consistency-based proposal learning module to compute the consistency-based proposal learning losses. So we could train object detectors on both labeled and unlabeled data. During inference, we only keep these blue arrows, so our inference costs are the same as fully supervised object detectors. Now let's dive into this semi-supervised learning losses. First is self-supervised proposal learning loss. The self-supervised proposal learning loss consists of two parts: proposal location loss and contrastive loss. For proposal location loss, the training target is to predict the proposal locations, like the coordinate of the top left points and the bottom right points related to the whole image. Here P is the ground truth proposal location and L is the predicted proposal location. Proposal location prediction requires proposal features understanding global image information to some extent, so we could learn context-aware proposal features by proposal location loss. For contrastive loss, we use softmax loss to enforce noisy proposal features to be closer to their original proposal features than to other proposal features, so we could learn noisy invariant proposal features from this loss. Next is consistency-based proposal learning loss. The consistency-based proposal learning loss consists of consistency losses for both bounding box classification and regression. For consistent loss for bounding box classification, we use KR divergency to enforce class predictions from noisy proposals and their original proposals to be constant. For consistency loss for bounding box regression, we use the standard bounding box regression loss smooth L1 to enforce object location predictions from noisy proposals and their original proposal features to be constant, so we could learn noisy invariant proposal features and predictions using this consistency loss. Using all these components, we could learn proposal features and predictions from both labeled and unlabeled data. Here are numbers to show that when comparing with the previous semi-supervised object detection method, data distillation or DD, our method improves different fully supervised object detection baselines by about 2%. In summary, our approach learns proposal features and predictions from both labeled and unlabeled data, and our approach improves object detection results by about 2% compared to fully supervised baselines. That's all. Thank you.